What we're going to do today is go through all the examples that we looked at for free body diagrams, and we wrote down all the equations, and now we're going to find all the forces and the accelerations if it's applicable. And what we're going to do is we're going to make the generalizations as shown here at the top, that whenever we have a mass, it's going to be 2.5 kilograms, coefficient of kinetic or static friction is going to be 0.15, the angle is going to be 17 degrees, and the tension is going to be 34 newtons. That should work for most of them. If it doesn't, I'll have to do a little bit of adjusting as we go along. So let's start off with situation 1. So situation 1, remember, is the object is just sitting on a stationary plane. We've got normal force up, gravitational force down, and the acceleration is 0. So for situation 1, redraw what I had. Normal force up, gravity down. The acceleration was 0, and our equation was that the total force in the y direction was normal force up minus gravitational force down, and that adds up to 0 because it's stationary. So that means the normal force is equal to the gravitational force, and gravitational force, remember, is always equal to m times g. We know m and we know g, so m is 2.5 kilograms. G is 9.8 meters per second squared. So just multiply that. We get 24.5, and the unit is newtons. Okay, we've got two significant figures and everything, so I'm going to have to round that. 24.5 gets rounded down, and so my gravitational force is 24 newtons, my normal force is 24 newtons, and my acceleration is 0. Okay, on to the next example. What was the next example? Now the next example was that we had the object sliding to the left at a constant speed on a frictionless surface. So again, we want to find all the forces and we want to find the accelerations. And again, remind ourselves what the situation was. It's moving at a constant speed, so the acceleration is 0. And the diagram is exactly the same as what we had before. So again, we've got the acceleration is 0, total force in the y direction is 0, and that's normal force up minus gravity down. And so we've got exactly the same thing as before. Normal force is equal to gravity, and that's equal to mg. So we've got 24.5 newtons again. Since all these examples have the same mass, it's going to save us a little bit of time. And so we'll round that to 24 newtons. All right, done the first two. What's the third one? Now the third one, we've introduced some friction, so it's going to the left and it's slowing down because of friction. All right, so let me write down what we had. Some of the forces in the y direction was 0, and some normal force minus gravity. The only other force we had was a horizontal force. So again, normal force is equal to gravity, mg, 24.5 newtons, and we'll round that off to 24 newtons. All right, what else do we have in the x direction? We've got frictional force, and that's equal to the mass times the acceleration. We don't know the acceleration, we do know the mass. Can we calculate the frictional force? Remember, frictional force by definition, kinetic frictional force is mu k times the normal force. We figured out what the normal force is, and we're given that the coefficient of friction is 0.15. So it's going to be 0.15 times the normal force, and I'm going to put in 24.5 newtons. Again, remember, when you're in the middle of a calculation, don't use your rounded off number. Use all the significant figures you have. So our frictional force is 3.675 newtons. For my final answer, I've got to round that to 2 sig figs, so that's 3.7 newtons. But for intermediate calculations, I'm going to use my value with all the sig figs. All right, so now I want to find the acceleration. I know mass times acceleration is equal to the frictional force, which is 3.675. So the acceleration is equal to 3.675 over the mass, which is 2.5 kilograms. And I get an acceleration of 1.47 meters per second squared. And again, I've got to round that to two significant figures. Get an acceleration of 1.5 meters per second squared. and the acceleration is towards the right, and I've got a positive number, so that looks right. Okay, what else? Next one, example 4. Example 4, now we've added in a tension. We're pulling over towards the right and slightly upwards. And remember, we said our angles were always going to be taken to be 17 degrees. And so our equations, let me copy them down here. I've got the total force in the y direction is 0 because it's not leaping up off the surface, it's not falling through the surface. And I've got two upwards forces now. Normal force in the y component of the tension upwards minus gravity downwards is equal to 0. And my total force in the x direction is the x component of the tension minus the force of friction is equal to the mass times acceleration. All right, can I solve for anything now? Well, I can get my gravitational force. My gravitational force is mg, so that's going to be 24.5 newtons. Again, round that to 24 for the final answer. Do I know my normal force? Well, I can't get it from here because I got to get my tension. Do I know what my tension is? Yeah, I know my force of tension is 34 newtons, and it's applied at an angle of 17 degrees, like that. So I need to find my x component and my y component. My x component is this side of the triangle, and this side of the triangle is adjacent, so that's ft cosine theta. So that's 34 cosine of 17. So it's 32.5 newtons. The y component is ft sine theta. So that's 34 sine of 17. So that's 9.94 newtons. Okay, so now I can look at my equation. So I've got, for my y equation, that the normal force is going to be the force of gravity minus the y component of the tension. So I've got my force of gravity, 24.5, and again, remember, put in your unrounded numbers, minus the y component of the tension, 9.94 newtons. So my normal force, 14.56 newtons. So I've got all the forces in the y equation. In the x equation, I need to find the force of friction, I need the acceleration. Remember, the force of friction, once I know the normal force, I can get it because it's just mu times the normal force. So I can do 0.15 times 14.56 newtons, and I get 2.18 newtons. Okay, so now we're almost there. So I've got my acceleration is equal to the total force in the x direction, ftx, which I know is 32.5, minus the force of friction, which is 2.18. So mass times acceleration is 32.5 minus 2.18, which is 30.32 newtons. So the acceleration is 30.32 newtons over the mass, which is 2.5 kilograms. And I get 12.12 meters per second squared. I've got to take all my things to two significant figures. So 14.56 rounds up to 15 newtons, 2.18 rounds to 2.2 newtons, and 12.1 meters per second squared rounds to 12 meters per second squared. Okay, so I've done the first four. I've got all the forces, the magnitude of all the forces, and I've got the magnitude of the acceleration for 3 and 4. Okay, let's move on to example 5. All right, remind ourselves, what's example 5? We've got a block sliding down a frictionless ramp. So the acceleration is down the ramp, and our axes are twisted. So let me draw on, for this case, our free body diagram. So I've got my normal force like this, gravity straight down, no friction. So those are the only two forces that I have. And the acceleration, remind ourselves, is down in the x direction. Okay, so what do we have here? Some of the forces in the y direction is 0 because it's not leaping up off the ramp or down through the ramp. And in the y direction, remember I had my normal force up and I had the y component of the gravity down. So that means my normal force is equal to the y component of the gravity. In the x direction, the only force I have is the x component of the gravity, and that's equal to the mass times the acceleration. Okay, so now I just have to break the gravity into components. So remember, if I draw my y-axis extended downwards, this angle in here, that's theta. So the x component of gravity is this side of the triangle. So that's Fg. X is Fg, sine of theta. So that's mg sine theta. So 2.5 times 9.8 times the sine of 17 degrees. Remember we said all our masses were going to be 2.5 kilograms, all our angles 17. And so I get 7.16 newtons. Fgy is going to be this side of the triangle over here. Fgy is adjacent to the angle, so it's cosine. So it's going to be 2.5 mass times g, 9.8, times the cosine of 17, which is 23.43 newtons. Alright, so my normal force is equal to Fgy. So that's 23.43 newtons. And 2 sig figs gives us 23 newtons. The mass times the acceleration is equal to Fgx. So that's 7.16 newtons. So the acceleration is 7.16 over 2.5 kilograms, which is 2.86 meters per second squared. Alright, so I found all my forces. Remember, Fg is still 24.5 or 24 newtons. Round everything to 2 sig figs, so Fg is 24 newtons. Normal force is 23 newtons, and the acceleration down the ramp is 2.9 meters per second squared. Okay, so far so good. Now we're going to do one where we've got an object sliding down the ramp, but now we're going to add in friction, and the friction, remember, points opposite to the motion, so it's up the ramp. I don't want to spend a lot of time repeating what I said before, so let me just copy down what the equations were. Okay, so I had some of the forces in the y direction were 0, and that was the normal force minus the y component of gravity. Some of the forces in the x direction were Fgx down the ramp and the force of friction up the ramp. Okay, so what do we have? So this tells us that the normal force is equal to Fgy, and it's exactly the same setup and exactly the same numbers as the previous example, so we know that's going to be 23.43 newtons, which rounds to 23 newtons. Okay, so see number 5 if you want an explanation for that. Fgx is equal to 7.16 newtons, again like in number 5. The force of friction is mu times the normal force, so that's going to be 0.15 times 23.43, which is 3.51 newtons. So the total force in the x direction is going to be Fgx, 7.16 newtons, and again, see number 5 if you need an explanation for that, minus 3.51 newtons, 3.65 newtons. And that's got to be equal to the mass times the acceleration. So the acceleration is 3.65 newtons over 2.5 kilograms, and that's 1.46 meters per second squared. Okay, so I've got all my forces, rounded to 2 sig figs at the end, so frictional force is 3.5 newtons. The acceleration is 1.5 meters per second squared. Okay, so we're done half of them. Let's move on to the next one. Alright, example 7. Now we have the opposite case to example 6. It's sliding up the ramp and it's slowing down. All right, so what equations do we have? In the y direction, it's the same thing. Normal force up minus a gravitational force in the y direction down is 0. So again, it's exactly the same as number 5 and number 6. And since our masses and angles are all the same, all the numbers are going to be the same. Normal force is going to be 23.43 newtons, or 23 newtons if I round it to 2 sig figs. The frictional force, well, frictional force is mu times the normal force. So again, since the normal force is the same as in number 6, we get the same number. So 0.15 times 23.43, which is 3.51 newtons. The total force in the x direction. Now remember, this time we've got normal force up, gravity goes straight down. The thing is sliding up the ramp, so friction is down the ramp. And the gravitational force in the x direction is down the ramp, so those two add together instead of subtracting like we had in the previous example. So I've got force of friction plus Fgx, so that's 3.51, remember keep all my digits at this time, plus Fgx, which is 7.16, so I get 10.67 newtons is my total force in the x direction. By Newton's second law, that's got to be equal to the mass times the acceleration. So the acceleration is 10.67 newtons over 2.5 kilograms, which is 4.27 meters per second squared. And let's round that off straight away to 4.3 meters per second squared. Okay, number 8. I can probably fit that one on the page since it's very simple. All right. In this case now, we've got the block is not moving, so the acceleration is 0. So the frictional force up the plane is balanced by the gravity down the plane. The normal force perpendicular to the plane is balanced by the gravitational force perpendicular to the plane. So my y equation is going to be the same as in 5, as in 6, as in 7. So again, you can see that once you've figured out how to do one type of ramp problem, you've pretty much figured out how to do them all. So normal force is equal to Fgy, and Fgy is again mg cosine theta, so 23.43, or 23 newtons, rounded to 2 significant figures. In this case, since it's static friction, we can't automatically say that friction is mu times the normal force. Remember, that's only true for kinetic friction. So what do we have? We've got that since the thing isn't moving, the total force in the x direction is 0, and that's equal to the force of friction in one direction and the x component of gravity in the other direction. X component of gravity, just like before, is mg sine theta, or 7.16 newtons. So the force of friction is Fgx, which is 7.16 newtons, and we go around that to 7.2 newtons. And I guess, of course, we need to put in what Fg is 24.5, or 25 newtons, and the acceleration is 0. Sorry, that should be 24 newtons. I round 24.5 down to 24. Okay, so now we're 2/3 done. Let's go on to the last 4 examples. Example number 9, now I've got the object being pulled up the ramp with tension, and it's increasing speed up the ramp. So now I've got 4 forces. I've got normal force, perpendicular to the ramp, tension up the ramp, friction down the ramp, and then gravity straight down, so that's at an angle to the ramp. And again, we're going to find the components just like we did before. The numbers are all going to work out the same. All right, some of the forces in the y direction's got to be equal to 0. What do I have in the y direction? Normal force up. Remember, my y-axes are tilted, so y is perpendicular, x is parallel to the plane. So normal force up minus Fgy down is equal to 0. And so now you see, again, we've got exactly the same thing that we had before for all the other ramp problems. Normal force is equal to FGY, so that's 23.43 newtons, just like as in examples 5, 6, and 7, and 8. So round that to 23 newtons. Force of gravity, of course, is mg, so that's 24.5 newtons, round to 24. What's the frictional force? Now the object's moving, so I can use kinetic frictional force, which is mu times the normal force, so 0.15 times 23.43. And again, that's the same as what we had in example 6 and in example 7. The frictional force is equal to 3.51. We'll round that to 3.5 newtons. In the x direction, total force in the x direction is the tension up the plane minus the friction down the plane minus the x component of gravity down the plane. So tension we said we're always going to use as 34 newtons. That's a given. Frictional force we just figured out was 3.51 newtons. The x component of gravity, just like in the previous examples, is 7.16 newtons. So my total force in the x direction is 23.33 newtons. And that's going to be equaled by Newton's second law equals ma. So A is equal to 23.33 over 2.5 kilograms, or 9.33 meters per second squared. All right, go through, make sure I've got everything rounded to 2. So normal force, gravity, friction, tension is given to be 34. So just round off the acceleration to 9.3 meters per second squared. Okay, number 9 is done. Number 10, now this is going to be an easy one because the thing isn't moving. So I've got, the object is just hanging from the ceiling, so I've got my tension up, I've got my gravity down, and the acceleration is 0. So that means the tension is equal to the force of gravity, and force of gravity is mg. So that's my 24.5 newtons, the same as before. We'll round that to 24 newtons. Okay, now we've got in number 11, another stationary situation. So the acceleration is 0, so it means total force in the x direction 0, total force in the y direction 0. But now we've got friction added into the equation and a normal force because it's on a surface. Okay, so let me copy down the equations that we had since we've already worked it out. The sum of the forces in the x direction was equal to the tension in the string down the ramp minus the force of friction plus mg sine theta. The forces in the y direction, I've got normal force minus fgy, so that's mg cosine theta, is equal to 0. Okay, so normal force is equal to fgy is equal to 23.43 newtons. And we'll round that to 23 newtons. My mg sine theta, I know that that is 7.16 newtons. So now I've got in the x direction, I've got that the force of tension plus the force of friction is equal to 7.16 newtons by rearranging this. Do I know what my force of tension is? Well, I don't really, because this thing is sitting on the rough ramp. The tension is not necessarily equal to 34 newtons. We know that it's not very likely to be 34 newtons because that would make the thing accelerate up. So all I know is that my force of tension is equal to the force of friction minus 7.16 newtons, and I can't solve it any further than this. So the initial parameters that I gave just aren't enough to exactly solve for all the forces in this situation. Let's go to situation 12. Now for situation 12, we had 2 blocks that were tied together. So let me remind you what we had. We had a simple situation for each of them. For block A, the normal force up was equal to gravity down. And we're going to assume that both blocks A and block B then are 2.5 kilograms in mass. So that means for block A, the normal force on it is equal to the gravitational force on it, which is equal to mg, which is just like before, 24.5 newtons. Round that to 24 newtons. The tension force, we don't know. We're going to have to do a little bit more math to figure it out. All right, for block B, we know that the tension in the cable minus mg is equal to minus m times A. And we had a similar equation for block A. We had that the tension in the cable was equal to the mass of A times the acceleration. So I don't know what the tension is because I don't know what the acceleration is, but I can take this equation and I can substitute it in over here. So I've got that the mass of block A times the acceleration minus the mass of block B times G is equal to minus the mass of block B times A. Now all our masses are the same as each other. Mass A equals mass B is 2.5 kilograms. So if I rearrange this equation, I've got MA minus MG equals minus MA. I want to solve for A, so let's bring both terms with A on this side. So I've got MA plus MA, so that's 2MA equals MG. You can see actually the masses cancel out on both sides, so I don't even have to do any calculations. So A is equal to G over 2, so that's 9.8 over 2, or 4.9 meters per second squared. Now I can go back and I can find my tension. The tension in the cable is M times A, so that's 2.5 times 4.9. Remember, we're asked to find all the forces as well as the acceleration, so I got to find that. And so the tension in the cable is 12 1/4, so we'll round that to 12 meters per second squared. Okay, so I've got my forces. Normal force, gravitational force on both of them are equal to 24.5 newtons, and the tension is 12 meters per second squared. All right, so we worked our way through all these examples. If you can do all of these examples and solve them, you'll have no problem doing any questions that are put on the test.